बॉक्स है ना। Hello, good evening. Let's wait for others for 5 minutes and then we can start. Okay.
Okay, ma'am.
Screen is visible. Good evening, all of you. Today we'll be discussing the techniques that are related to find out the interaction between an enzyme and its substrate. Okay. So enzyme substrate interaction, to find out, there are many different techniques that we will be talking today and solving the question that are related to that. Okay. So first technique here, the question it has been asked from the exchange matrix. Okay, so first I'll tell you what is a ion exchange chromatography. So ion exchange chromatography is a type of chromatography method or type of purification of your desired protein, where you can uh, select the protein based on their charge that they possess. Okay, so suppose your protein is either your protein could be either positively charged or negatively charged. Okay, and now you want to from a population of different negatively charged protein, you want to select only your desired protein which is positively charged. You can use this chromatography, which is ion exchange chromatography. Okay, ion exchange chromatography. So here what happens, you allow your protein mixture to pass through a column which is having a matrix which is charged. Okay, so in the column your matrix is either positively charged, okay, or the matrix could be negatively charged. Okay, so yeah, yeah. So these are two types of matrix, of column matrix. So here the positively charged matrix you use to uh, purify the negatively charged protein, and the negatively charged matrix you use to purify the positively charged proteins. Okay, so what happens here in the column, these matrix are already loosely bound with some ions. So if it is a positive charge, obviously it will bind to a negatively charged ion, right? So for example, here this positively charged matrix loosely bound with chloride ion, suppose. Okay, chloride ion. This negatively charged is bound with sodium ion, like this. Okay, so when the your mixture of protein comes here, okay, the negatively charged protein of your interest. Okay, so what happens then? There is a exchange of ions happens in the matrix. So this protein of your interest will replace this chloride ion and bind it in a matrix. Okay, so the chloride ions will be replaced and occupied with the protein. Oh, sorry. Okay. Similarly, in this case, sodium ion will be replaced or exchanged, and the positively charged protein will bind to the matrix. Okay, so this is how the binding of your desired protein happens. Okay, so in the first question it has been asked, okay, so here the exchange of anions are happening, so that is why this will be called as anion exchange chromatography. Okay, anion exchange. And here the binding or the exchange between the positive ions are happening, that is why this is called as cation exchange chromatography. Okay, so in anion exchange chromatography the exchange of anion is happening, and for that purpose your matrix is positively charged, and here in the cation exchange your matrix is negatively charged. So whatever an exchange chromatography it is, the opposite charge will be on the matrix on the column. So based on that this question comes that dash is an anion exchange matrix. So in order for it to be a anion exchange matrix, it should be of positively charged or negatively charged. If it is a anion exchange matrix, whether it will be positively charged or negatively charged? Try to think. Please answer.
Positive charge, ma'am.
Yes, in because it is involved in anion exchange. So for that purpose, the matrix should be negatively charged so that the negative charged anion can be exchanged. So among all these, the positive charge is present on the Sephiroth matrix. So, and all the others are negatively charged. So that is why the correct answer will be Sephiroth. Okay. Next question, if we'll see. Yes. Come to this later, maybe. Yeah, this is another question from the ion exchange chromatography. Okay. So here, what they have given, here they have given that there is a protein which is having an isoelectric point or pi value is 5.1. So first tell me what is pi or isoelectric point. What is isoelectric point? Isoelectric point of any protein is given. What do you mean by that? So, so here I'm asking what is the isoelectric point of a protein? Here in the question it's given that there is a hypothetical protein and the pi of that protein is given, which is 5.1. What do you mean by that 5.1? Okay, so I'll tell you. So isoelectric point is nothing but at which the charge on the protein becomes zero. The pH at which the charge on the protein becomes zero, or it is present in its Zutter ion form, like both positively and negatively charged, and at the pi value or the pH equal to pi, the protein will likely to precipitate. Okay, so it will not be soluble anymore if you are taking any buffer and putting your protein in that buffer, and the pH of that buffer is equal to the isoelectric of that pH point of that protein, then the protein will precipitate in the buffer. It will no longer remain soluble in that. Okay. However, if you will go above this pi or below this pi, so above the pi your protein will be negatively charged, and below the pi the protein will be positively charged. Okay, because okay, so this is the pH. So pH above pi, the protein will remain in negatively charged. Why? Because in the pi, okay, sorry. So generally at this particular pi, what happens? Protein remains in this form, H2 plus and COO minus. This is the R group. Okay. So when the pH is higher, the hydrogen ions are less. At lower pH, more hydrogen ions are there. Okay, more positively charged hydrogen ions are present. Okay, so then what happens, the protein or the amino acid tends to accept the ion. So this negatively charged carboxyl moiety will accept the this free hydrogen ions and will become like this H. It will form COH. Then the net charge on the protein will become positive. So the protein, when goes to a lower pH, it becomes positive, and then when it goes to higher pH, it tends to release more hydrogen ions. So in that case, it becomes COO minus. So then the net charge on the protein will become negative. Okay. So that is why. So let's read the question first. So it is given that a hypothetical protein is isolated from the bacteria using DEAE cellulose column to purify the pure protein. Okay. The protein is allowed to bind the column for 30 minutes, followed by elution with appropriate buffer. What pH range of elution buffer cannot be used to elute the protein from the column? So similar ion exchange chromatography they are doing. So here they have taken this matrix which is DEAE cellulose. So this DEAE is the full form is there A denotes amino. So amino means positively charged. Okay. So positively charged is their matrix. So their matrix is positively charged. Okay. The protein is bound here. This they have done, and the protein's pi value is 5.1. Just give me 2 minutes. Live. Yeah. So this is the question. So the isoelectric point of the protein is given, which is 5.1, and the protein is being isolated using DEAE column, which is a positively charged column. To purify the protein, the protein is allowed to bind for 30 minutes, followed by elution. So what should be the pH of the buffer to elute? So as I already mentioned, the pH above pi, if you go the pH above pi, the protein will present in negatively charged form, and below pi, the protein will become positively charged. Okay. So here if you want, now in order to elute the protein, what you want this protein to leave the matrix, and in order to leave the matrix the protein should be positively charged. Okay, so suppose if you add a buffer of pH which is lower than of its pi value, so pi is 5.1 and you lower it, the pH, the buffer of the pH should be less than this pi. Okay, suppose you added a buffer of pH 4. Okay, and then what happens, all these protein will become positively charged because now the buffer pH is below its pi, and that makes the protein positively charged. And when it becomes positively charged, what happens, it will leave the matrix and come out of the column. Okay, come out of the column and leave the matrix. Okay, so here the options given to us is, yeah, so the question is, what pH range of elution buffer cannot be used to elute the protein from the column? So if the pH of that buffer is greater than pi, then it becomes negative. So or it remains negative, so that pH we should not use. So the pi is 5.1, and if anything which is above 5.1, that is not suitable for the elution. So 2.5 to 3.5 can be used, 4 to 5 can also be used, 3.2 to 4.5 can also be used, but this 7 to 8 cannot be used. So at pH 7 to 8, the protein remains in negatively charged, and that is why it will remain associated with the matrix, and then in that condition the protein cannot be eluted from the column. Okay, have you understood my point, or do I need to explain again? Is it clear? Is it clear, people? Please say yes or no. Or did you understand or not? Anyone? Okay, now I'll ask you people to unmute yourself and tell me. Okay, Shuchika, do you understand the concept or do I need to explain again? Shuchika? Yes, okay. You got it. If you want, I can explain it again. Okay, do you want to me to explain again? What is your doubt? You can unmute and tell. Okay, okay. Okay. Yeah, so this is done. Yeah. So choose the correct option for ion exchange chromatography. So there are four options given. So yeah, so I have already told what is the concept. I would like you to answer. So first option I am reading. So pH greater than pi, the net charge on the protein is positive and bind to cation exchange. So if pH is greater than pi, then the net charge on the protein will be what? Positive or negative? Positive or negative? pi above and below pH. So the pH above than pi, this side, what will be the charge? Positive or negative? Unmute yourself and answer. Please interact.
Good
Good
afternoon,
afternoon,
ma'am.
ma'am. Sorry.
Yeah, ma'am. Good
Yeah, ma'am. Good
afternoon.
afternoon. Yeah. Please answer the question.
Yeah, ma'am. pH greater than pI, I think it's -1
Yeah, it will be negatively charged.
because
And
of less positive hydrogen H plus ions.
hmm,
So when pH is lesser, it has greater hydrogen H plus ions.
hmm.
So I think
Yes. So I told you. I think you didn't join that time, or I don't know. So
yes,
at
yes, ma'am. I think this is my first class, ma'am.
okay.
Yeah,
Yeah.
previously
So
I tried to join, but I didn't, ma'am. Because of college times, I'm unable to join.
okay, no problem. So
Yes,
at
yes.
pi, what happens? The protein remains in its zwitter ion bond. That means both positive and negative charge will be there. Okay. So when the pH increases, or suppose if pH decreases, so at lower pH, what happens? More positive ions are there, right? More hydrogen ions are there. So in that case, what happens? This COO group takes up those hydrogen ions. Okay. More hydrogen ions at lower pH. Okay. So that time it becomes like this: COOH. This accept the H, and then the net charge become positive here at lower pH. However, at the higher pH, the tendency to lose hydrogen ion for the amino acid becomes more, and then this looks something like this. Okay, then the net charge becomes negative. Okay, so the uh, pH at which is higher than the pi, the proteins remain in negatively charged form, and the pH which is lower than the pi, the protein remains in the positively charged form. Okay, so here the first option is pH above pi, the net charge on the protein is positive. Okay, so but here it will be negative, right? So this option is
Yes,
incorrect.
ma'am.
Yeah,
Yes,
this option will be incorrect. And next is pH less than pi, the net charge of the protein is negative. pH less than pi, again it should be positive, right? Yeah. And if it is negative, it should not bind to the anion exchanger. If it is positive, it should not bind to the cation exchanger. It is the opposite binding. Or no, sorry, it's nothing. So this is also wrong. Then third option is pH is equal to pi, the net charge on the protein is positive and bind to the cation exchanger. No, at pH which is equal to the isoelectric point pH, the net charge on the protein is 0. That is why there is no charge on the protein. That is why this option is also wrong. The fourth option is pH above than pi, the net charge on the protein is negative, which is correct, and binds to the anion exchanger. Yeah, yeah, this will be correct, because if the protein is negative, the matrix will also be positive charge. Then in that case, the anion exchange happens, and these kind of matrix will be called as anion exchanger. So the correct option will be D. Okay. Next, we have this option question, which is a solution present in a 1 centimeter cuvette transmits 40% of the incident light. What will be the concentration of the solution? Given that epsilon, or the molar extension coefficient. So this can be solved based on the Beer-Lambert's law, which is A is equal to ECL. So A is absorbance, right? E is molar extension coefficient. C is the concentration, and L is the path length. Okay. So this is Beer-Lambert law. I hope you know that. So here we have been asked what will be the concentration of the solution. The concentration we can find denoted by C. So in order to find out C, we need to know the E, L, and A. So E, we know that uh, we know that molar extension coefficient, which is given here. L is the path length, which is 1 centimeter cubed. That L is given. Okay. And now we need to know the absorbance. Okay. So to find out the absorbance, we have a formula. So here we have given as 40% of the incident light being transmitted. It is not being absorbed. So we have to calculate what is the absorbance. Okay. And to calculate the absorbance, the formula is log I naught upon IT. T means transmitted light. So log, this is total light, which is 100%, and transmitted light is 40%. Okay. So the value will become 2.5. Log 2.5. So you have to find out the value of log 2.5. We'll see log 2.5. It is coming 0.3979. So the value is coming 0.3979. Okay, log 2.5. So that is the absorbance. So you just need to keep it in this formula. A 3979 is equal to E, which is given. You also need to check the these things that the unit is also correct or not. So it is given per molar per centimeter. Okay. So E for the unit of E is calculated as E is equal to, it comes A upon C L. So absorption has no unit. So C is unit and L is unit. So C is molar, L is centimeter. Then the unit comes per molar per centimeter. Okay, so that is how the unit is coming. And in the same unit, the answer is also being asked. It is not micromolar or millimolar. So you have to take care of that also. If those little variation in the unit are also given, so you need to keep everything in the same unit. So, but here it is all the same. So this is the A, and then E is 6,000 into C that we need to find out, and L is 1. So your concentration will be 3,979 upon 6,000. Okay, so that will solve this. Just coming 3,979 into 6,000. It is coming 2387. 2387. Yeah, it is coming as, I'll write here, it is coming 0.6631. Okay, this is the value we are getting, and we can also write it as 0.63 into 10 to the power. So will become -1. We'll come back to this question again. Something is wrong. Yes, yeah, the value is coming this. is coming something like this. This will be the correct answer. Maybe I'm doing something wrong in the calculation, but this will be coming to this calculation. Similarly, if we'll see the next question also, it is given that monochromatic radiation is incident on a solution of 0.08 molar concentration. So the concentration is given 0.08 molar of an absorbing substance. The intensity of radiation is reduced to half. Okay. So intensity of radiation is reduced to half. That means 50% is being absorbed or 50% is being transmitted after passing through the 6 centimeter length solution. So L becomes 6 centimeter. What will be the molar extension coefficient of the substance? So again, here you need to calculate the absorbance. So I naught by I, 50% is being absorbed, then it becomes 100 divided by 50, that comes uh, divided by 50, it comes 2. So log 2 will be 0.3010. So it will calculate like that, 3010 divided by 0.0826. See what answer we are getting. Exclusive 0.26. So I'm getting this answer. Which I'm getting here. Okay, so this is how this formula and the Beer-Lambert-Rov is A is equal to ECL can be used to solve this kind of question. Okay, next we'll see. So the pair of technique which does not employ the labeling of biomolecules to study their interaction. So here the first technique is SPR and NMR. So SPR is surface plasma resonance and NMR is uh, some other technique where you cannot study the interaction. So here it has been asked to study the interaction. So SPR is being used, but not the NMR. Then we have ITC and FRET. In FRET and FRAP, both what we have a fluorescence coming out of the system that can be detected. So for fluorescence, the tagging or the labeling of the biomolecule is needed. So that is why these two options also become wrong. The third option is SPR and ITC, isothermal calorimetry and surface plasma resonance. Using these two techniques, we can study the interaction of the proteins and know labeling also of the biomolecule is needed. So correct option will be this. Next, we'll see the ligand X bind more tightly to a protein than ligand Y. If so, here what happens, it is, for example, an enzyme plus substrate complex. So the forward reaction which makes enzyme substrate complex is K1. And then we have the reverse reaction which is K inverse. Okay. And then we have K2 which is enzyme plus product formation. Okay. So our binding affinity is equal to K1 and K inverse. So the higher the association and lower the dissociation, more will be the binding affinity. Okay. So this is, you can also refer as Ka and Kt. So the lesser it will be the dissociation of the enzyme substrate complex. If it is more, then it will be the substrate will keep on releasing from the enzyme and the product formation will not be happening. So that is why for more affinity, the dissociation constant will be lower or should be lower. So the ligand X bind more tightly to a protein than ligand Y because the ligand X has a KD value which is lower than the ligand Y. So the correct option will be option B. So next we have to match the appropriate elution strategy with their respective chromatographic techniques. So these are the different chromatographic techniques. Okay. First is size exclusion chromatography. So this we can, first option is varying ionic strength that does not match with the size exclusion chromatography concept. So in size exclusion chromatography, what happens? You have a column where you have beads, okay, and then you have proteins to separate. So you have protein of smaller size and bigger size, okay. So what happens here? Using size exclusion chromatography, you can separate the protein based on their size. So the smaller protein will enter the bead and will take more time to travel through the bead and elutes later. However, the larger one will come out from the void space and will be eluted first. So here, no buffer will be needed of varying ionic strength. So the first is not matching. Then we have methanol AC ingredient, which is the polar solvents which is being used for the reverse phase chromatography. We have the fourth option, which is isocratic gradient, which is the constant buffer or constant composition of buffer is being used. So that is matching with the size exclusion chromatography. Then we have ion exchange chromatography, we just now talked. So there varying ionic strength of buffer is being used. So for example, you at the end of the protein, you at the end of the chromatography, you want to elute the protein. So there what you do, you give the elution buffer of very high ionic strength so that the protein will leave the matrix and eluted with the buffer. So an ion exchange will be first, and then we have nickel anti-column chromatography. So in nickel anti-column chromatography, what happens? We have a competitive binding with the imidazole. So nickel anti-column chromatography, this resin is bound to a protein which is histidine tagged, and that nickel anti is also can also bind to imidazole. So similarly, as I have mentioned for the ion exchange, when you give high concentration of imidazole, the his-tag protein will leave the nickel anti and it will be purified, leaving the other non-specific protein behind. Okay, so these are the, and reverse phase will be matching with this. Yeah, all are marked. This is a image of sensogram. So sensogram is obtained using a technique which is surface plasma resonance, SPR. Okay. So in SPR, what happens? You have a gold plated sheet which is enzyme is attached to that sheet. Okay. Then you have a liquid flow chamber. Okay. There you flow the liquid and along with that you give substrate also. Okay. And that substrate can go and bind to this enzyme. So once the substrate where you have the incident light that will be given here and will be reflected back, and here we put a detector. So if substrate is not bound, there will not be any change in the angle of the light being reflected. However, when the substrate is bound, the change in the angle will be absorb. So that when plotted against the intensity of the light and the angle, so then when the substrate is bound, then you will find that there is a dip in the graph. Okay, more substrate will be bound, more dip in the angle will be observed. Okay, and that you can plot here in the form of resonance signal. So more dip, more curvature in the increasing manner you can see in the graph. And then what happens when the enzyme becomes saturated, then you remove the substrate from the, or you pass such buffer that is without substrate. Then what happens, the substrate will come out of the enzyme bound matrix. Then the peak will be in the opposite direction. Okay, and that again scored via the this drop. And then again, if the enzyme becomes free, again the substrate can start binding, which is observed by this. So here the A will be the association. Okay, or you can also say A is K on. A is not regeneration, not dissociation, not analyte binding. So yeah, so A is K on. B is the when the saturation reaches, that is called steady state. C is the off or denaturation or dissociation, and D is the regeneration of the enzyme substrate complex. So that is a sensogram that tells you the interaction of the enzyme and the substrate which is given via the liquid chamber. Okay, so the correct option will be C. Okay, this is another question from size exclusion chromatography. So size exclusion chromatography is performed under different conditions based on the chromatogram. What will be the oligomeric status of the protein in its natural environment? So as I have already mentioned, when you perform size exclusion chromatography, the proteins of bigger size will elute out first, followed by the protein of the smaller size. Okay. So here the chromatograph is or the size exclusion chromatography are done at two different conditions. So the red line is only the protein uh, is given, and the protein has come at very early retention time. Okay, here the peak has come, and if the and now the protein with beta mercaptoethanol. Beta mercaptoethanol, what it does, it breaks the disulfide bonds between the proteins. Okay, so here you can see this peak is not coming in the blue sample. Another peak is coming. One came and followed by another. Okay. So two different peaks at two different points are coming. That means one of the protein is of higher size, subunit is of the higher size, another subunit is of the lower size. And because of that, they came at the different size at different time points. Okay. So and two peaks are coming. Based on that, you can say that there are two uh, subunits and both are coming at different uh, retention time. That means the sizes are different. Sizes are different means the unit or subunits are totally different from each other. So based on that, you can say that it is a heterodimer. Okay, and when without beta ME you were running the size exclusion chromatography, only one peak was coming, which is of the entire full length protein. So the protein is considered as heterodimer. Okay, I hope you understood this. If you are having any doubt, please ask me, stop me in between and ask me the question. Okay, another is a protein shows 180 kilodalton band in native page, and when the same protein was run on STS page, it shows intense band corresponding to 90 kilodalton. So native page we perform when the native page is performed where there is no change in the native structure of the protein. Protein is being run on the gel electrophoresis in its native form. Okay, so in that case, it is coming as 180 kilodalton. However, when you are running on STS page, so STS is a denaturing agent. It breaks the bonds or denatures the protein and divided into corresponding subunits. Okay, so then you can see the 90 kilodalton band, only one band. That means 90 kilodaltons, two units are being associated together and forming a total 180 kilodalton protein. Okay, 90 plus 90. Okay, then you are finding when the protein was run on reducing STS page. Reducing means again reduction of the disulfide bonds. Okay, then the protein shows two bands of 50 kilodalton and 40 kilodalton. So 50 plus 40 is equal to 90. So each 90 kilodalton subunit is divided into two subunits, which is 50 plus 40, 50 plus 40. Okay. So the actual protein looks something like this. So 40, 40, bigger size 50, 50. So it is two different units. these these two associated with disulfide bonds. That is why when giving the reducing page, their interaction is being broken. So the nature of the protein, homotetramer, no, even though it is a tetramer, but all the units are not same. That is why it is not homotetramer. Then we have heterotetramer. Yes, it is a tetramer and it is different kinds of unit. That is why heterotetramer. It is not a homodimer. It is not a heterodimer as well. Okay, it is a 4 subunit protein. That is why it is a heterotetramer. So the last question is yes. So a ligand that binds more tightly to a protein than another ligand, probably because it has same thing which I've explained earlier, this point. Okay. So if K1 is greater than K inverse, the binding is very favorable. So this you can also say K on, this you can say K off. So if K off is less, the binding is favorable. So if one ligand binds more tightly than another ligand because it has a fast, slower kinetic off rate. This should be low enough in order for the binding to be strong or favorable. Okay, and yeah, even though the kinetic on rate is fast, the kinetic off rate is also fast, then there will be no point, net it becomes zero. Then that is why the faster the kinetic on rate and slower the kinetic off rate. That should be the exact scenario in order for the ligand to bind the protein tightly. Okay, so these are the all questions which I had today. If you want to ask anything, you can ask me now. Any doubts? Or I will conclude today's session.
Ma'am?
Yes,
Yes, ma'am. So where I can get all these recorded classes, ma'am?
I will upload the recorded classes, but still in the live session also you try to interact, try to ask question. There are not many people, few people only, so you can interact. Otherwise, I will upload all the recorded videos and slides on the NPTEL portal itself. Okay.
Okay, ma'am. Ma'am, how will be the paper, ma'am? The toughest or the type of asking the questions, ma'am, in question paper?
It will be the same, like whatever sir is teaching in the class, similar to that topic, only the question which I am telling you. Okay. So these kind of questions will only come. So you have to practice this and also the assignments which is given by sir.
Yes, yes, ma'am. Some of the assignment questions are somewhat tougher. I couldn't even get through transcript. given
Okay.
transcript.
Mhm.
So that the reason we are losing the marks, ma'am. So what
Okay.
will be
So
the minimum marks to get qualify in those assignments, ma'am?
uh, that I don't know. Maybe I need to ask that. I don't know that. Okay. So, but still,
Okay,
if
okay,
you
ma'am.
are like not confident in some of the question, you can bring them in the class. Okay, like in the live session. Maybe we can discuss them and
Okay,
solve
ma'am.
them. Okay.
Okay, ma'am.
Yeah.
Yeah.
Okay. Thank you. Okay, so I'll conclude
Ma'am,
today's session.
every week, when
Yeah.
will be the class, ma'am? Live sessions?
This live session is every week, Friday from 6 to 8.
Okay, okay, ma'am.
Okay, you must be getting
Yes,
the
ma'am.
link and also the reminder, weekly reminder on your registered email ID.
Yeah, ma'am, I'm getting those links. But
Yeah,
first when I joined, it showed that no one are there in the class except me. So that's
okay.
why I just left, ma'am. I
No,
thought
but that
classes are
is
not
not the
going
problem.
on.
No. Classes are going on. People are not coming. So I waited for 30-40 minutes, but nobody joined. So I concluded that day's session. So maybe try to come on the time because 6 o'clock I start the live session. Okay.
Yes, ma'am. Okay, ma'am.
Even though nobody is there, you be there. Try to solve your doubts, bring up your doubts, and we'll discuss them and solve them. Okay.
Okay, ma'am. Okay, thank
Yeah.
you, ma'am.
Okay. Thank you. Bye.